So that's just all right. So my name is Zach Shwira-Conti, and I'm a research associate at the Alan Turing Institute here in London. And I'd also like to introduce my co-host and co-organizer of the seminar series, David Masagur. Hopefully I got his surname correct. So David is one of our new co-hosts, and he's also a new PhD enrichment student here at the Alan Turing Institute. So for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. And also, for the benefit of those joining us for the very first time, I'd like to briefly introduce this topic, the topic of the seminar series, which is physics-enhanced machine learning for engineering applications. So physics-enhanced machine learning, as most of you know, is an upcoming subfield in machine learning and deep learning, and that aims to integrate known physical understanding of observed phenomenon into the machine learning framework. And of course, the advantages include data efficiency, interpretability, which are important factors if we want to take machine learning into the applied world. So also on a side note, if any of you out there are interested in sharing your work with us and with this community, please do get in touch with us, and we'll be happy to communicate with you and guide you into doing so. So as for the format of the seminar, first Jan, who's today's speaker, will share his work with us, followed by a Q&A session, which you may do so either through the chat, or you can also ask your questions in person. So without further ado, I'll ask my colleague David to introduce our speaker for today. And with that, I thank you all.
Yep, thanks. Yeah, as you know, we have here today Jan Povala presenting for us today on this very exciting topic. Jan is a postdoctoral researcher at the Alan Turing Institute, working on an innovative AI system for air traffic control. Okay. Before this, he recently earned his PhD in statistics at the Imperial College, investigating models for spatially correlated data. And he collaborated with the Metropolitan Police Service on crime modeling. Before all this, he also worked as a software engineer at Amazon. And his main interests are computational statistics, uncertainty quantification, modeling of spatially varying phenomena, statistical models of urban environment, and Bayesian inverse problems for partial differential equations. So yeah, thank you very much, Jan, for offering this talk. And yeah, I shall hand it over to you to start the presentation we'll look forward to.
Yeah, thanks very much for the kind words. So this the topic I'm going to be talking about today is second part of my PhD, and it was done in collaboration with Yeva and people at Femi Chirag's lab and Mark Girolami, who was one of my supervisors during my PhD. So the topic we're going to be talking about is how to it's more of an empirical assessment how variational Bayes can be used for Bayesian inverse problems involving partial differential equations. So I'm guessing most of you guys are engineers, so like you don't need motivation why PDEs are useful, but I'll just mention briefly anyway. Many phenomena in science and engineering, they are better modeled as some sort of rate of change rather than absolute values, and partial derivatives encode. They give us a way of encoding how a quantity changes as we move through a domain, space or space-time, for example. And they are mechanistic, and they provide an interpretable way of specifying relationships. And this hopefully goes with the theme of the seminar series, where we actually have some physics together with the data-driven approaches. So this is something that you guys know a lot more about than I do. So I am a computer scientist by training, and I am new to kind of applied mathematics, but PDEs have been used throughout in fluid dynamics, modeling elasticity of materials, heat systems, electrostatics, or kind of the go-to example that everyone uses is the Poisson equation to model the steady state flow of groundwater flow through an aquifer. And so kind of so PDEs have been around for a while, but what has changed recently is the amount of data we have. And the question is, okay, what do we do with it? So, just to give you a real life example. So this is stolen from, well, stolen. This is taken from someone else's work. So it's a real life example. We have a railway bridge in Staffordshire, and that has been instrumented with fiber optic sensors to measure strain. And the idea is that we build a model, and then like the one on the right hand side. So we have a mesh, and then we collect the measurements from these sensors, and then we try to use it. So kind of how do we use how do we like once we build this digital twin, and how do we use it? So what we can do is first thing that it's useful for is kind of asking what if scenarios. For example, what would happen if, I don't know, the train had twice as much cargo as it did, as it normally does. And where the data comes in is in two ways. So either used for calibration of the models, or we can also use it as a way of finding out properties of a system. So for example, like if we have an elasticity problem, we do a tensile test, we might want to use the measurements of displacement and using the Hooke's law to find out the properties of material. So this second problem, where we use the measurement of the system to infer the system's properties, is the inverse problem, and it's kind of it is the focus of this work. So for the rest of the talk, we will very formally say what the Bayesian approach to inverse problem is. Then we will discuss variational Bayes as an alternative to MCMC, and then as part kind of our main contribution is how leveraging the problem structure can make variational Bayes method effective. And we've got some experiments on simple PDEs, and also like also we include a bimodal example, and then we conclude. So this is probably the most boring part of the talk, but I thought I would mention it anyway. So we have a mapping from the parameter space, which is the curly K, into the observation space, which is curly Y, and then we have this mapping from K to Y, and then into the observation space, and then we have some observational noise, and then kind of to build in a PDE model into this. So what we do is we choose a suitable Hilbert space U, and then we have a solution operator A, which maps the parameter, which is a map from the parameter space to the space U, and for a particular parameter kappa in the curly k, the solution is given by this operator A. And to map it into the observation space, we define a projection operator U, which maps from the U space to the observation space. And so this equation 1 can be kind of expanded into this form, where A is the solution of a PDE for a particular parameter kappa, and then we have the projection operator, and then we have the noise. And the overall objective is to find kappa, which is in the parameter space curly k, given the observations in the which are observed in the observation space. And so the observation is a noisy observation of the solution of a PDE. Okay, so hopefully this makes sense. If there is any questions, let me know. This is very much, so I guess a lot of you are familiar with this Andrew Stewart way of formulating things. So this follows very much the same even notation. Just to give you an example, what we're doing. So we have the Poisson equation, and so we have our parameter kappa is the log of diffusivity, and so for a given forcing function for the given right hand side, and then for a given diffusivity here, the solution of the PDE varies, and then we observe the solution of this solution U usually at the finite number of points, and we want to, based on the knowledge of F and based on the observations of U, we wanna infer the kappa here. So one thing to notice here is that, for example, if you look at the green curve here and the blue one, which is constant, set at 1, so it is two radically different functions. But then if you look at the solution space, it results in not two dissimilar solutions. And I should have mentioned the boundary conditions here are set to equal 0 on both ends. And yeah, I should have said it like this is on a unit line. This is what we're dealing with. So the way we usually go about this is we try to find kappa so that the data misfit term, where we have the observed data y, and then what the model suggests, we try to minimize with respect to kappa. So what usually happens is that y is finite dimensional, and the kappa we are interested in is a function, so it's infinite dimensional. And so this is an ill-posed problem in general. There may be no solution. It may not be unique, or it may depend sensitively on the data. And so we need some sort of regularization to proceed. So there are more traditional ones, such as Tikhonov regularization. What we do here is we follow the Bayesian approach, where we put in the prior knowledge we have about kappa in terms of a prior probability measure on the subspace of the curly k space, the parameter space, and then we use the Bayes formula to obtain the posterior probability measure mu y for kappa given the data. So this is all very abstract in general. Yeah, this is not, this is even more, this is still fairly abstract and technical. So that the relationship between the posterior and the prior measure is expressed as follows, where this d mu y divided by d mu naught is the Radon-Nikodym derivative of the posterior measure with respect to the prior measure, and the phi is the potential function, and that's determined by the noise, the observational noise eta, and then by the operator, by the mapping from the parameter space to the observation space. So to make things a bit more concrete, we assume that the observation space is finite, and from here on we treat y and eta as like finite dimensional vectors. In general, they don't need to be, but in practice they are usually. And we assume that the additive noise is Gaussian wide noise with standard deviation sigma y, and this allows us to write the potential function as follows, where this gamma matrix is a diagonal matrix. Okay. So in terms of the prior specifying kind of restricting the solution space for the parameter, we put a we restrict the space of solutions to be a Hilbert space, and we place a Gaussian prior measure on kappa with mean m and covariance operator c kappa, so such that mu naught follows Gaussian measure. And then kind of here we have two ways of going about things. So we are at the point where we are able to do inference, and we are dealing with infinite dimensional objects here. So kind of two ways of doing things. So first we can derive the inference procedure, not implementation, procedure on the infinite dimensional space, and then we discretize when we implement the scheme. Or we can follow the approach of discretizing first and then deriving the inference afterwards. So this is more just a reference, like a set of references that people can have a look at. So this is the first approach where we develop an inference scheme on the infinite dimensional space. Here, the most common approach is the precondition Krag-Nicolson MCMC. It's one of the algorithms we used as well for benchmarking. And then there has been some more developments. For example, MCMC methods that leverage the geometry of the posterior is this reference. And then there have been some attempts to develop variational Bayes methods in function space, and here are some references, but it's still not quite there. In terms of the discretized first approach, so this is more familiar to all of us, and we basically discretize the what we are interested in, the kappa, and then we follow one of the usual approaches. For example, we can do MCMC methods such as Metropolis Hastings or HMC, or we can do Laplace approximation, or we can do variational Bayes methods, which is something we do here. So this brings us to the more familiar formulation of the Bayes theorem rather than this one, which is the Bayes theorem in the infinite dimensional space. So we have this we have the posterior for the kappa given the data, which is proportional to the likelihood py given kappa times the prior on kappa. And we can now specify what exactly these ones are. So the likelihood term involves solving the PDE, and so just to illustrate this, we work with the already mentioned Poisson problem. So again, we have kappa is our log diffusion, so log diffusivity or conductivity, depending on the context. And then we have forcing, which is deterministic. And then what we do is we formulate the weak form of the problem, and then we discretize using standard finite element approach with the Lagrange basis functions, as shown here for 1D and 2D examples. Then we can express the solution as using coefficients UI. So, and then overall, by discretizing the stiffness matrix and the right-hand side, we get the linear system as follows, where we have the stiffness matrix, which depends on kappa, and U is the coefficient of our solution given by this, and then we have the discretization of the right-hand side. Just for completeness, this is how we compute the elements of the stiffness matrix. I'll skip those, and this is the right-hand side discretization. And after we put everything together, this is our likelihood term, where we have the P is the discretization of the observation operator that if you remember from the beginning, the curly P we had, which maps the solution of a PD into the observations. So, and then the solution of the PD basically is the solution of this linear system that we had here, AU equals F. And then we assumed Gaussian noise. So we have the diagonal covariance matrix because they are uncorrelated. And so this gives us the likelihood. Now the prior, so we assume zero mean Gaussian process. The way we discretize kappa was by assuming that kappa is constant on each element of the mesh, and then the centroids of the elements are the training points of the GP, and we have so the prior is multivariate Gaussian normal with the covariance matrix given by evaluating the covariance function in the training points. And the covariance function itself has two parameters, the length scale and the amplitude. We fix the amplitude for our experiments, and we experiment with the length scale. So now we've got the likelihood, we've got the prior. We are now ready to proceed with the inference. So what we do is we follow the variational Bayes approach, where we posit the family of distributions from which we choose the minimizer of the divergence between the posterior and the family of the so we try to find the member of the family that has the lowest divergence, KL divergence with the posterior. After some manipulation, the problem in equation 17 is equivalent to the maximization of this term, where we have the KL divergence between between the distribution we're trying to find and the prior, and this is the this term is evaluating the likelihood with respect to the expectation of the log likelihood with respect to the Q distribution. So this is generally not available in closed form. This scale term is often available in closed form, especially, well, it is available in closed form for example, like when P and Q are both Gaussian. So, but this term is not generally available. So what we can do is we can approximate it using a Monte Carlo approximation, and it turns out that we need very few number of samples for the method for the whole optimization to be effective. And we've got some experiments to show, kind of to confirm what the literature says on this. So as you can imagine, everything depends on the choice of the variational family, or this curly DQ, as that sort of gives us flexibility. So we want to choose something that is flexible enough, but also computationally tractable. And kind of what most people do is they usually choose Gaussian distributions because it is convenient, and so do we. And there is we experiment how we parametrize our Gaussian distribution, and so just kind of mentioning it for completeness, there are a few other things one can do. For example, we can choose a mixture of variational densities when we have multimodal posteriors, or kind of more recent approaches include kind of hierarchical specification of the Q of the distribution of the approximating distribution Q. And then so if you're interested, like I would look at these two references. So kind of maybe like is everything clear to everyone? Maybe it's a good time to take a, because I only see my full screen, and I don't even so I wanna make sure like everything is clear to everyone.
Yeah, if anybody has any questions, you feel free to sort of ask in the chat.
Yeah.
It will pop up.
Okay, so it might not pop up for me, so Zach, if you
don't worry, I will let you know.
Okay. Yeah, just shout. Okay, so as I said, the multivariate Gaussian parametrization is a very convenient choice, and we've got a few options, especially with regards to the covariance function. So the first choice is choosing diagonal covariance matrix. This is very efficient and quite easy to implement and easy to optimize. And yeah, I mean, the only problem is like we're not capturing dependencies between the variables. And then we can go to the other end of the spectrum, where we optimize so we break down the covariance matrix into Cholesky factors, and then we like what we optimize over is the mean and the components of the Cholesky factor. And the other option is using precision matrices, which using the precision matrix, which is the inverse of the covariance matrix. And it's something that we advocate for here in this work, and I'm going to talk about it a bit more now. So specifying the multivariate Gaussian to the precision matrix means that we are specifying the inverse of the covariant. Sorry. What the elements of precision matrix mean is that if the component of the precision matrix is 0, it means that the two components of the random vector, so component I and component j of the random vector are conditionally independent, and the conditioning is on all the other variables other than I and j. Whereas for the covariance matrix, we have if the covariance made, and this is of course only for Gaussian random variables like this. If the covariance matrix element is 0, it means that they are independent. And yeah, if you're more interested in more details about precision matrices, this book is really good. So just to give an example, so we have a 5-element mesh. Well, no, it's not exactly mesh. I mean, it's a unit line split into 5 elements. We can, so in terms of choosing which components we want to have as independent, we can choose it based on the problem. So given that we use finite element specification, we've used that structure to inform our how we specify the non-zeros of the precision matrix. So if we represent each of the random variables corresponding to each element as nodes of a graph I, j, k, l, m, then we can build a connection the way the edges the way we want. So like the obvious choice is to build an edge if they are neighbors. Then another option is if they are second order neighbors, meaning they are a neighbor of a neighbor. So, and then once we build these edges, we can kind of get the adjacency matrix, and then this adjacency matrix gives us the non-zeros of the precision matrix. And then this is just for an illustration. If we have a 2D mesh like this, we build an adjacency matrix, and then we get something like this. And of course, this is not looking great because it's not exactly a bounded matrix. So what we can do is we can reorder the elements and then we obtain the matrix with a much lower bandwidth. And this is the basis for specifying the precision matrix, the Q. And so we use the fact that the bandwidth of a matrix, sorry, if the bandwidth of the full matrix is, let's say, B, then the bandwidth of the Cholesky factor of that matrix is less than or equal to B. So so if you have, so by using, we have the adjacency matrix here, then which has bandwidth, well, I don't know the number, but basically we can create the non-zeros, which is this one, and then we fill in the full bandwidth. Sorry, not the full bandwidth, the bandwidth that we obtained from this adjacency matrix, and then this gives us the Cholesky factor. I'm not sure if I explained it clearly, but if we can discuss more if you have questions. So yeah, this is the way to specify non-zeros of the Cholesky factor of the precision matrix, and yeah, that's all there is to it. And yeah, so I'm gonna talk quickly, so I've got about 20 minutes left. So I want to go quickly through the experiments we've got. So I'll focus on the 1D Poisson problem. And then, so we, as mentioned before, we are trying to infer the posterior distribution of kappa given measurements of y. So we have, this is a synthetic experiment. We put the sensors on the discretization nodes, and then the sensor noise is 0.01, and then we take 5 readings from each sensor. And then we assume constant forcing, and then we have the Dirichlet boundary conditions. And the way we generated the true kappa was by sampling from a Gaussian process with squared exponential covariance function with length scale L kappa equals 0.2, and the amplitude was 1. So these are the, so here we have the results. So in this row, so the second row of this figure, we have the gray dots are the measurements that we obtain, and then we are trying to find the posterior distribution of kappa, which is in the top row. So we the red curve in the top row is the true kappa that was used to generate the data, and the black curve with the blue shades is the black curve is the posterior mean, and the blue shade is 2 standard deviations of the posterior mean, sorry, of the posterior for kappa. And so what you can see, so as the gold standard, as the standard we compare to, we have Hamiltonian Monte Carlo, and then preconditioned Cagnicals and MCMC. So these are MCMC methods, which are we have theoretical guarantees of I mean convergence in the limit, but I mean implementing these is not trivial, but we use them as the benchmark, and so we can see that the full covariance parametrization gives very similar estimates to the HMC and PCN method. And kind of on the other extreme of for the variational Bayes methods, we have the mean field variational Bayes, which captures the mean very well, but then doesn't incorporate doesn't estimate uncertainty whatsoever. And then we have something kind of halfway house, which is the precision variational Bayes method that we've been advocating here for, and where the uncertainty estimate is not as good as the full covariance parametrization, but it's much better than having a diagonal covariance matrix like we have here in the mean field variational Bayes. And then below we have the same thing, except that the prior for the kappa was matching the prior for the length scale of kappa was matching the true length scale that was used when generating the data, and same conclusions apply as to the above panel. Then we've also tested how well these methods do in terms of uncertainty propagation. Let's say we are interested in a specific quantity. So we compute the log of the total boundary flux through the left boundary, and then we plot the posterior distribution of that. So what's for these two, for the two panels on the right, we see that the mean field variation of Bayes is is too centered and doesn't doesn't capture uncertainty at all. On the left one, this is we suspect this is a problem with the optimizer where we have a local optimum which we found, and as you can see, the precision variational Bayes method is underestimating uncertainty as well. Anyway, so for the other two, with the precision matrix parametrization, we can get good uncertainty propagation. Here, like, is a few results to show that when you increase the number of sensor readings, we get the behavior that we expect, i.e., our uncertainty estimate decreases, and the same happens when the sensor noise is decreased. So it collapses to the true value of kappa that generated the data. Then a few more experiments. We also show that these figures show the posterior for kappa, and with the increasing number of samples of the log, when we estimate the expectation of log likelihood, and we can see that after 5 samples there is not much difference, especially for this precision matrix parametrization, which is the last one. So this is kind of confirming what people are saying in the literature, where sometimes they even do with 1 sample. Another experiment we did was increasing the bandwidth, i.e. increasing the neighborhood structure, considering more neighbors. As expected, with the increasing number of neighbors, we can capture more dependencies in the data, when this reflects in capturing the uncertainty better. But we can see that, like, with the difference from 2 to 10, there's a significant improvement, but like from the difference between 10 and 20, the difference is not as big, so there's some sort of saturation going on. And this is more just a quick kind of argument about, again, empirical argument for using variational Bayes methods as opposed to MCMC methods. What we have here is basically the runtimes that of different methods, and we can see that variational Bayes methods, they are an order of magnitude faster than HMC methods. Sorry, than MCMC methods. So I'm gonna skip the 2D experiment because it's exactly the same, and the same conclusions apply, so that we have time for questions. And I'm just gonna mention, this is almost like a toy example, but we wanted to show that you can use it in setups where the posterior might be multimodal. Again, this is almost useless in practice, but just I'll quickly go through it. So we have a metal rod with unknown conductivity properties. It's constant throughout, and then we have a uniform heat source throughout the rod, and then temperature on the right hand side here is fixed but unknown, and then on the left hand side we know it, and then so it's fixed and we know it. So it's like a boundary conditions, and then we obtain 2 readings of temperature here in the center. And the question we are trying to ask is, what can we say about heat conductivity of the rod and the temperature on the right-hand side? So just to give you an idea of how basic two different combinations of conductivity and the right-hand side condition temperature can lead to the same measurements. So we're taking measurements here in the middle, and we can see that if we increase the conductivity, which is then basically we would expect that if the conductivity is high, then so will the temperature on the right-hand side. So what we can do is we can kind of express this knowledge in the prior, which is as follows, and then we can do inference by positing a mixture distribution for the approximation, and then we can get a posterior estimate as follows. So this is not this is more to demonstrate that, okay, you can, if you believe that the posterior is multimodal, you can do that with variational Bayes methods. And in terms of implementation, so I want to give credit to people in Femi's lab. They've got the C++ code that they let us use, and we've only written the variational Bayes part in TensorFlow in Python, and our Python code calls out to the C++ code. And so yeah, our code is available on GitHub, and we've got a paper for this that was accepted recently. If you want to know more details about this. So just a quick summary. The variational Bayes methods provide an accurate point estimate for the mean of the posterior. Depending on the parametrization, they can also be an adequate estimate. They can provide adequate estimates of uncertainty as measured, as compared to HMC and PCN. Specifically, the sparse precision matrix is especially relevant because it reduces the number of parameters we need to optimize, and is still able to capture the dependencies in the posterior distribution. And in kind of computational argument goes that it's about an order of magnitude faster than HMC or PCN methods that we've implemented. And then also in terms of propagation of uncertainty, we've shown that it is effective in that respect as well. There's quite a few things one can do. So there's nothing stopping us from doing this for more complicated PDEs. So it will be quite good to do it for more relevant more examples. Then we could also consider stochastic forcing. So one thing that I want to mention is that at the moment, the precision matrix parametrization is useful in the sense that we reduce the number of parameters we need to optimize. But as you could see here, the computation times for the full covariance parametrization and precision matrix parametrization, they are comparable, and that is because we were using we were not using sparse computation, because that's something that is not available in TensorFlow, and we so the reason, the only advantage that we had from the sparse precision matrix was reducing the number of parameters. So it's quite a limitation, but there should, we didn't want to kind of do these things manually, so we wanted to use a framework which was available. Yeah, so that's all I have. So I'm happy to answer any questions you guys have. Thank you for your attention.
Thank you very much, Jan, for your very elaborate presentation on your work. If there are any questions, please put them in the chat, or you may also unmute yourselves. In the meantime, I was actually hoping to see if potentially, I was wondering if you actually did apply this to the bridge example you showed in the beginning, which I believe pertains to Femi, right?
Yeah, so no, so we wanted to, and it should be possible, and but it was I mean, it was during my PhD, and I was trying to finish my PhD quickly, so it was more kind of like, let's get something working.
The question is because I was wondering whether nonlinearity in measured phenomenon, like from that bridge, for example, so this is not noise, right? It's maybe noise coming from actual behavior nature, whether that would influence the calibration robustness of your method.
I think the only way to know is to try, I guess.
Yes, for sure.
So I don't know. I know that some people are picking things up. So in the Femi's lab, some people are working on kind of similar things. So maybe we will see it one day. But no, we haven't tried it on a real example.
Right.
And yeah.
But in terms of like non-linearity of the phenomenon that you are dealing with, even in the finite element model, how does this influence the variational approach in terms of calibrating your reach?
So I guess it will show up in terms of harder optimization and kind of more nasty optimization surface that you're optimizing over.
Would this influence the shape of the distribution that you would be looking at?
So I mean, so there is two components, right? So there's the prior and the likelihood. So and then the type of PDE you are dealing with is encoded in the likelihood. So it will, I think it will show up in the likelihood, right?
Right. I was simply asking, like, just to understand whether this would impact the robustness of the method. That's all.
I mean, like as we also said in the paper, like we believe it shouldn't, and it should be fine. I mean, so what could be problematic is kind of the shape of the optimization surface. So I really, I can't really say more than that because we haven't tried. So but in terms of kind of theoretical limitations, we don't should be fine. Like there's nothing stopping anyone from doing things, but in practice, who knows?
All right, I think we have thanks for that.
I have a question.
Yes, okay, go ahead, Tommaso.
Hi, Jan, thank you for your presentation. It's very interesting. Can you go back to the bimodal example? I didn't understand which kind of distribution you used which space of distribution you used to represent kappa in order to get the bimodal.
Yeah. So for the Q, so for the approximating distributions, we had two bivariate, so a mixture of two bivariate Gaussian.
Okay,
and
so you need to make an answer on the number of modes you expect to find.
Yeah. So and this is very artificial example. So
it's very important.
We knew that we expected that to be two. Well, we expected there to be two modes.
Okay.
And we simply so all we had to optimize was the mean. So the mean of both components, and then
also the variance of them,
and the variance and the covariance as well between the two.
The cross correlation, yes.
Yeah. So yeah, exactly.
Okay. All right. Nice. Thank you.
I do have a couple of questions if we have time still.
Mm-hmm.
Yeah. First one, I'm not a fully expert in the variational Bayes and inference, but can you actually go through again where do you apply the adjacency matrix you were explaining before? You were having two different levels. Yeah, that's the one. Where does it come into play then?
Yeah, exactly. So you need to so we are trying to find Q, which is a distribution from a space of distributions, and basically we choose the Q here. So the space we restrict the space of approximating distributions to multivariate normal, and then this is the Cholesky. So here we specified the multivariate normal through precision matrix. So
okay,
and LQ is the Cholesky factor of the precision matrix.
All right. So basically, you need then the adjacency matrix to get the Cholesky factor then.
Yeah, exactly. So so the way you build it is like this. So you have your mesh, then from this mesh you get the adjacency matrix, like if the two nodes are adjacent, well, if the two elements are adjacent to each other.
Yeah.
Then what you can do is you can reorder your vector, you can reorder your kappa, so that the adjacency matrix is banded.
Yeah.
And what you do then is that basically there is a result in linear algebra which says that the bandwidth of the Cholesky factor of a banded matrix is less than or equal to the bandwidth of the full matrix, right?
Okay. And that bandwidth is going to be actually wider if you are using two levels of connectivity, no, rather than
absolutely,
one.
Yeah, absolutely,
yeah,
absolutely,
okay.
yeah, absolutely. So from here you can basically, if this one has bandwidth, let's say 10, probably more anyway, like let's say 20, you know that the Cholesky factor will have bandwidth less than or equal to 20. So, but just to be safe, you fill in everything, right? because like, for example, here we have zeros,
okay.
but like we need to fill it in because we don't know. It could be non-zeros in the Cholesky factor.
Okay. And then my other question is about if you can give a feel of how many, evaluations of the PDE you need for this method to work.
Yes.
So actually, how much training data you need? Okay, do you have a feel on that? Or
So
is it very problem dependent, I guess, as well? Or?
So here we are. So we need to, if you look at this optimization problem, there's maximization of this elbow term, like evident lower bound. So this term doesn't need a PDE solve. So this one is, and it's available in closed form. So this one is easy.
Okay.
The problem is here, because we have this expectation of the log likelihood, and each log likelihood evaluation requires a PDE solve.
Yeah.
So what the term, so that's why we also did experiments on how many samples you need to approximate this expectation. So it turns out you can keep it quite low, but you still need to, let's say if you choose NSVI equal to 3, then each optimization steps will require 3 PDE solves, for example.
Is it just PDE solves, or is it solution and gradient?
And the gradient as well.
Okay, so yeah.
Yeah, because we use the gradient based optimizer.
Okay.
Okay, and in any case, I guess this is order of magnitudes less than using a Monte Carlo.
Yeah. So
method, no?
when we use the Hamiltonian Monte Carlo, we need to get one sample from the posterior. We need I mean, it depends, because it depends on these number of leapfrog steps. So for each leapfrog step, we need no, let me think now. I forgot. Like, I would have to check, but like basically there's more PDE solves because they may be harder to tune and they take a while to converge. So, but I would have to check if to obtain one sample. Let me think now. Okay. Actually, so I forgot how HMC works, but anyway, I would have to look. But anyway, overall, it's a order of magnitude faster. So
yeah. Okay. Thanks, Jan. Thank you. Very interesting.
Right. Yeah. I think we'll wrap it up here, because I think Jan also would like probably tired from talking. But I would to say actually congratulations to Jan for defending his PhD just last week, I believe. So congratulations.
yeah, thank you.
Okay. Congratulations, then.
Thank
We can call you doctor. All right. Thank you again, Jan, for your work, sharing your work, and thanks everybody for the questions. And we look forward to our next talk. Hopefully everybody will hear about it soon. So until then, have a great day and a great week.
Yeah, thanks everyone for joining in.
Bye.
See you guys. Bye.
Bye. To seeing you at the end meeting. Bye.